Hello. So if I can get you to stop, collaborate, and listen, I'm going to be talking to you very briefly about demand capacity modelling that I've been doing in mental health. My name is Simon Wellesley Miller. I'm Information Manager at Devon Partnership Trust. I've worked as an analyst for about 12 years now, previously in child protection and the police, but for the last 6 months in mental health. I've been trained in modelling by Pencord, which is our medical department in the local university, and also currently taking my master's degree in data science for healthcare at Exeter University. Just to say, this stuff is not really super scary, and it really is just using our data in a really positive way to actually come up with proper solutions to sort of some of the real world issues, and not just popping KPIs into pie charts, which is what we tend to do. So, looking at our problem, community waiting lists have been increasing due to various factors. They weren't terribly great before COVID. Obviously, COVID hasn't helped that at all. So yeah, that's part of the why. What we obviously need to do is reduce waiting times to improve services for patients. But part of that is really understanding where to put that additional resource. With any sort of pathway or any system, we could just reduce our waiting lists by adding in sort of loads of front end assessment work just to get people off of the waiting list, which would kind of work to up an extent, but it would also create this massive tsunami of patients through the system, which would just flood the system going forward. So that's not really what we want to do. And also what we want to be able to do is actually sort of show impact and sort of trajectories of if we do this, this will happen, and if we will do this, this will happen in a sort of actual measured and proper way. So how are we going to achieve this? We are going to do something called demand and capacity modelling. Oh, don't worry about him. So what is demand and capacity modelling? Basically, it is modelling demand and capacity, but basically trying to actually marry those two things up and see what impact that actually has on systems. So this is something that's sort of really sort of coming to the forefront now, to actually understand much better sort of trajectories and what's going to happen going forward. It's also really good for sort of like bids around service improvements or service expansions. I've done some work around those to actually say, well, actually, if we do invest this, where do we need to invest our money, or how are we going to improve the service, or actually where are those bottlenecks, and where do we need that extra capacity? So big questions. So yeah, does variation in demand capacity, where and what impact does it have on our treatment and waiting times, which I'm sure is a very similar story across many services. And also, as I said, working out where to put those resources, because just chucking everything at triage would reduce our waiting times on that front end, but would just obviously flood the system going forward, which we want to try to provide the best sustainable treatment pathway for our patients as possible. So for all you Star Wars fans out there, we're going to start off with a little bit of a Q theory. So we are just going to talk through a couple of systems just to try to get your head around some of the sort of complexities that sort of demand and capacity modelling is, but in a really simple model which we can work through within our heads, hopefully. So we're going to have a look at a perfect system. And we're basically going to have 4 referrals come in regular as clockwork every day. And we're going to look at our referral rates over 5 days. So 4 referrals coming in every day, which gives us a mean average of 4. In order to service our 4 referrals, we have 4 slots available per day. So whether that's 4 clinic appointments, 4 doctors, for basically our capacity to deal with those referrals is 4. So we've got 4 referrals coming in and 4 slots available. We have a target that everybody has to be seen the same day that they are referred. And the target is set that 90% of people need to be seen on the same day as they are referred. And people also have to be seen in the order that they are referred. So prediction times, based on that information, and we have our 4 referrals, 4 slots, everybody coming in. Will we meet our target after 5 days? So we'll have a look at that one in a minute. We're also going to just add a little bit of variation into our system and see what impact that has to our system. So beyond that, we're going to look at an average of 4 referrals come in per day. And this particular week, they just happened to come in 5 on the first day, 4 for the next 3 days, and then 3 at the on the last day. So still 20 referrals over the week, and still a mean of 4 referrals coming in every day. We still have exactly our same 4 slots, still have all the other same criteria. So again, prediction time, are we going to meet our target after 5 days? And then finally, just twist it around, we'll have a slightly different week. Again, we'll still have our average of 4 referrals coming in every day, but this week they're going to come in 3 on the first day, 4 for the next 3 days, and then 5 on the last day. So still 20 referrals over the week, and still a mean of 4 referrals. We still have our 4 slots, and yada yada yada. Everything else is exactly the same. So again, prediction: will we meet our target after 5 days? So this is all about the importance of variation, and hopefully working through this example will show that. So let's pop back to our very first one. So we've got our 4 referrals coming in, regular as clockwork, and we've got our average of 4. So let's see if we can sort of visualize this. So we've got Monday, and there's our 4 slots, our 4 doctor slots available on that day. And there's our 4 referrals. So our 4 referrals come in, and that referral gets assigned to a GP. That one goes to a doctor. That one goes to a doctor. And that one goes to a doctor. So we have 4 referrals, 4 slots. Each of the referrals sits nicely in a slot. No problem. Tuesday, we have our slots go straight in again. Wednesday, Thursday, Friday, we have all our slots, and everything just goes through perfectly. We have exactly 4 referrals coming in, and we have exactly 4 slots. As we can see, every color is for a different day, and everybody was seen on their correct day, so we're all good. So 20 people were seen on the day they referred, 100% performance. Hooray. So let's just look at that again with that ever such a slight little twist of variation. So this week we're going to have 5 coming in on the first day, then 4, then 3. That's it. Still 20, still an average of 4 per day. So there's our referrals, all coming in per week. So Monday we've got our referral going across, and then that one goes in there, and that one pops there. And there we go. And then obviously we've got 1 left over, which unfortunately has to carry over till Tuesday. So that one goes over to Tuesday. Then we start seeing Tuesdays. And, oh, hang on. Oh, no, we still got 1 left. So that one has to go over to Wednesday. And hopefully what we start seeing, or you can start seeing, there's a little bit of a pattern forming here. That one goes over there, and that one goes over there. Basically, by the end of the week, we still have everybody will have been seen, but looking at whether people were seen on the correct days. So this guy, this dot, this referral, this referral, this referral, this referral were not seen on their days. So actually, only 16 people were seen on the day they referred, which gives us a performance of 80%, which is obviously less than our target. So we did not achieve our target. Also meant that we had 4 patients who were not seen within their time scale, so that's quite significant. Again, just very, very quickly looking at that with the variation looking the other way. So again, this week we're going to have 3, then 3 plus 4, and then a 5. So let's have a look at this one. Here's our referrals for the week. So there we go. Our Monday referral comes in. That referral goes to that slot. That referral goes to that slot. Okay, fair enough. We've got a slot left over. That's fine. These guys all leap over to their slots. And then Friday, we have a look at that. That one goes there. That one goes there. That one goes there. And then by the end of the week, actually, 19 people were seen on the day they referred. So we've hit target, which is fantastic. However, hopefully the astute of you will notice the elephant in the room. that we do still have one referral left over, which, in essence will mean that we will start next week instantly in that same position on a back foot, to add into that system. So that will cause us some problems. Be aware that I've been talking about waiting lists, but this can work for beds as well. So you can look at bed models and what demand capacity is required for sort of beds as well, not just sort of community teams. So we're either looking at capacity. Capacity can be workers required, slots are required, or beds, or potentially anything. Yeah, I think there's been some modelling around sort of COVID jabs and how many jabs are going to be required, etc., to meet those referral numbers and that referral variability. So, very handy acronym, which hopefully we can learn out of this, which is the DUNWANA. I think I'd probably need to work on that. The DUNWA, I don't know. Anyway, DUNWA, do not use averages. So I think I've seen in my time many models worked on that very base principle of, oh, we've got an average of this coming in, therefore we need to have that many workers. We've got our average of 4 referrals coming in, therefore we need 4 slots to manage that. And I think hopefully my little dots flying around my PowerPoint emphasizes and just shows really clearly that is, so far from the truth, and it will go wrong. So do not use averages. So what have we learnt? Variance is absolutely the key in understanding sort of demand capacity and queue times, whether that's the number of beds available, putting people in sort of outlier beds, whatever. That variance of your referrals is really important to get packed and to understand. Let's say overcapacity cannot be saved or banked. So on that second example where we had those 3 referrals, we had a day where we had a slot left over, but it wasn't of any use at all. You can't bank it, you can't save it. It's not useful. So overcapacity is not useful. However, and I think this is probably much more clear. Capacity really leads very quickly to queues, and those things kind of bounce off each other, and you'll just get into the spiral of extreme queueness or requiring further beds. Like I say, this example, look at waiting list, exactly the same principle for beds. And then you understand that to sort of demand capacity, there's a kind of a sweet spot of capacity that you need to service your demand. And like I said, that can be sort of calculated to a range, which is generally around 60 to 80%. But again, it depends on how volatile your system is. Often talk about NICE guidance for bed occupancy, which I believe is set at 80%. And that, again, that isn't quite often it's sort of mentioned that that's all to do with staff safety and various other bits and pieces. After lots and lots of digging, trying to work out where that number came from, it literally does come from demand and capacity, and then making sure that you have got capacity within your beds in order to meet that variation of demand. So that's where the magic 80-85% NICE guidance for bed occupancy comes. All this is backed up by sort of various bits and pieces: NHS Improvement, NHS England, NHS NICE guidance, and there's obviously a big national demand and capacity programme, which also does sort of some quite nice, simpler modelling, much more sort of overview modelling than the stuff that we are going to be doing. And there's some details there and some there. So how can all of this lovely demand capacity modelling help us? Let's say really using this as a sort of a data science to actually inform decision making. I mean, so often, as I said, we see those models which are built on averages, and they are just doomed to fail. So actually, we can actually use our data to properly inform decision making. That said, I've spent a year working with Pencord, actually university, and like I say, also currently doing sort of data science. And also was really lucky to sort of learn how to create these sort of models in using discrete event simulation, and also really lucky to sort of join up with the strategy unit to also promote and support discrete event simulation, which is what this project is. So what does this look like? And here is one I prepared earlier. So I'm not going to go through the actual code per se, but I will go through some of my model and some of the modeling work that I've done, just to show some of the bits and pieces that can be done. So I've created a very, very simple adult community mental health treatment waiting list model. I'm not going to go through all the massive details, but it worked on a really, really high level. It was very, very simple. It basically created a referral. Based on that referral, it then checked if there was any capacity available within the teams as a whole. If there was capacity available, it would seize that capacity. If it wasn't available, it would put that patient onto the waiting list. And then soon, so going down, if there was capacity available, then they would basically hold that capacity for the length of time that somebody was within that team. And then once that treatment was over, they would release that capacity, which would then sort of come back up here. And then that released capacity would then be taken up by the next person on the waiting list. And so it just sort of reiterates through. So relatively, as simple a model as you can possibly get to. And I'm sure we will come back to that at a later date. That absolutely the whole keep it simple. Create the most simplest model you can that will answer the question that you're asked. It's very easy to go down rabbit holes and go, oh, but Martha comes in on a Tuesday and she's a little bit late, so I need to make sure that comes in. And then Wednesday's afternoon is training day, so they've got half a less thing for that. And then, oh no, the wingle wrangle machine sometimes breaks down on a Thursday because such and such uses it, so we need to. So you can get really, really into sort of minutiae detail of what's going on, and yeah, you need to make sure you don't do that. I can't believe I said wingle wangle. Right, let's skip that bit. Anyway, so looking at this, I did some very sort of basic baseline analysis, looking at the daily rate of referrals coming in. So again, really, really nice to sort of actually sort of picture that and look at that referrals. Again, so, within my system here, I do have an average of 12.7. But again, you can sort of see, hopefully you can see for that there is, it is relatively normally distributed, but there is quite a spread of those referrals coming in. So, going back to my lovely dots flying around, that spread and distribution of referrals could really, really mess up a system if that wasn't pulled through. What was really difficult and trying to understand was sort of trying to calculate capacity available within a system. So rather than looking down at individual workers and FTEs and how much capacity has each individual worker got, I think I just tried to calculate it as looking at it as a system. We have a thing where we have patients on caseload and they might be on several. If they're quite complex, then they might be on several different clinicians' caseloads. So I think I tried to, again, just try to simplify it as absolutely as much as possible and just look at within our system how many patients are open at one time. And I would kind of use that as our capacity available. If that's how many patients that they can deal with at any one time, kind of pull that through as a capacity. The other thing we need to know is based on obviously once somebody's in the system, how long are they utilizing that capacity? So how long are they in the system? So again, had to do a bit of analysis around that. Quite difficult with mental health because quite often patients are, on the books, as it were, for sort of potentially several years. And obviously, when you're modeling, you're probably modeling up to sort of a year, 18 months, and possibly up to about 3 years. But obviously, further and further you go into the future, more fuzzy any sort of prediction is going to be. So, and your confidence levels around your prediction just get wider and wider and wider. So, kind of got to I tackled it in a way that, well, what percentage of those patients would get kicked out, not kicked out, would be discharged from the system within a certain amount of time? And anything that was over that, then we just kept it. It may as well, whether it was 2 years or whether it was 8 years, it was more or less infinity as far as the modelling was concerned. And again, sort of try to model that length of stay, and look at what that looks like. And again, it was a really, really sort of skewed and long-tailed distribution. So again, sort of modeling that into there. And I think we're looking at sort of trying to understand those distributions and how to statistically describe those, and add that into your model is definitely what we looked at. And then basically ran that through sort of the simmer, and came up with a very sort of basic baseline, as in, well, if things go as they are, what do we expect to see? So we looked at sort of service utilization and also sort of queue length. So if things carry on as they are and running it over sort of several different iterations, what do we expect to see? And I think it pretty much showed that should things stay as they are, then we would expect to see the even, there's a bit of a warm-up period, but after a while we would just see a very slow and steady increase into that waiting list, which obviously we don't want. Obviously, the beauty of creating really, really wonderful models is once you've created them and you've got your sort of your baseline sorted, then you can ask all those lovely what if questions, so and then tweak things accordingly. So one of the things that we're quite interested in, we were expecting an increase in referrals due to sort of COVID surge. So actually, what would happen to our system if we saw a 12% increase in our referrals? Which again, I think it quite clearly shows that our waiting list would massively increase, which is obviously understandable. What would happen if we had an increase in capacity? So whether that's a 10% increase in capacity due to improvements in productivity rather than actually sort of throwing more actual physical capacity. What happens if they manage to sort of streamline some of their processes in order to increase capacity by 10%? I think it showed that there would be some sort of quick gains of getting some people out of the system and discharged, but then there would be a very much slower and gradual decrease, mainly because there were so many referrals coming in. What would that do? And then my third scenario, what would happen if we had that increased capacity, but also that increase in referrals? So you kind of can build it up very, very slowly. So if things stayed the same, we showed that the capacity increase in capacity, we would see a reduction in the waiting list. By having both of those, unfortunately, the 12% increase in referrals and 10% increase in capacity was not sufficient to keep things in a steady state, and we would start seeing again that increase in waiting list. A further scenario was to add an increase into the discharge rates, so whether there was additional sort of step down available, or whether there could be sort of further details around sort of people who've been on the caseload for a long time and sort of building some extra pathways for them. So we looked at that. In of itself, it didn't make a huge difference to the model, mainly because, as I said earlier, we're looking at the model in quite a short length of time. We only sort of went up, 2 years in the model, sort of trying to predict 2 years in the future. So this wouldn't have had such a major impact. I think that it would have been one of those impacts that if you're removing people who have sort of reached 5 or 6 years, then obviously it's going to take 5 or 6 years before those people start coming off, before that has a sort of a visible impact. I wasn't happy of trying to do my predictions that far in the future again, because it would have, I can't imagine that things are going to stay stable and still and sort of 5, 6 years in the future. We're ever changing. There was also an additional service being created who was going to look at some of our long waiters, some people who've been waiting the longest, and see if there was sort of alternative details that they could go through, whether they could signpost to other services while they were waiting. And this was just us approximately taking about 50 referrals being diverted and discharged. And by doing that, again, we are sort of seeing a slow but steady decrease in the waiting list. And then there was a very final, complete new pathway for patients. So hopefully you can kind of see that, where there was a complete additional rapid reassessment where 30% of patients would go into this rapid assessment and be instantly or discharged from that. Then there was a new treatment pathway where about 50% of patients would be eligible for a phased treatment, and they would go down a separate pathway. Of those patients who go through this more rapid pathway, they would expect to about 50% of those to be discharged at that section. And then 50% of them would then go onto the standard pathway and then would go down this normal sort of pathway, as it were, and then be discharged. And obviously, throughout all of these things, they would also obviously sort of link up to the waiting list too. And again, sort of implementing that, and should it work as it says on the tin, that did show a really good reduction in the waiting list and sort of stabilizing the system quite quickly. However, that's obviously it was very theoretical, and obviously it would take a lot of work to actually get that into progress. So, and there's conclusions and recommendations. So let's go back to. So hopefully that gives you a very quick oversight of the of discrete event simulation. Hopefully just show you a very quick worked example around where that works, and you know the kind of things that you can show. I think there will be some other examples coming up, but yeah, any questions at all, let me know. And thank you very much. Very excited for you. You're going to learn some great stuff. So on that, I will leave you. Thank you very much.